Hello guys, this is Saeed Mohammad Waqas. The topic which I'm going to discuss today is related to the combined stormwater and sanitary system design. As you can see that there I have prepared an Excel sheet for this combined stormwater and sanitary systems design. So this is the drawing which I'm going to use, and I will calculate the pipe size of each segment represented here on the drawing. So these are the tables which I'm going to use during calculation. So first of all, you can see here we have a pipe mark. You can see that I have divided each pipe segment and give it a name. So here it is represented by a pipe mark, and then we have a fixture unit, then we have a demand, and then equivalent drain area in a square feet. Since this is a combined stormwater and sanitary system, we need to convert this fixture unit represented here on the drawing, because this fixture unit is from the sanitary drainage system. We need to convert this into equivalent drained area and write it here in this column, equivalent drained area. So for stormwater, is you can see that we directly here we have a roof area in here that is going to be drained is 4,000 square feet, and here it is represented 3,500 square feet. But we need to convert these fixture units into the equivalent drain area, and we can write in here. And then you can see the pipe breakdown. That means if you see in here this pipe section C, since the flow is from point A, flow is towards the point C, so flow at point A and point B. So flow at point C, it will be the sum of point A and B. So we're gonna calculate up till point Q, and we'll do the sizing up till point Q. So we're gonna start from this furthest outlet 256 fixture unit stack P2 point. So first thing over here, important thing is here the location. So where are you going to perform this one? Because rainfall rate is different for each city in the country, or different in different countries. So first of all, we have to check the location. Since I'm talking about New Delhi, India, so first I have to get the maximum rainfall rate in inches per hour in New Delhi. So there I have table here for 72 different cities in India. So since you can see that rainfall per hour, this is for 1 hour, this is for 3 hours, this is for 6, and this is for 24 hours. Since I'm talking about New Delhi, per hour rainfall rate in centimeter is given here. So as you can see here, its rainfall is per hour is 11.17 centimeter per hour. So if I want to convert this into inches, how much it will be? 11.17 divided by 2.54, that means 4.39 or 4.4 inches per hour. So that's how I write here 4.4 inches per hour for New Delhi. So for different cities, almost 72 cities data is in there, you can choose the cities. So here the procedure for combined storm water and sanitary drainage system, there's a procedure that which we need to follow as per standard, that if you have less than or equal to 256 fixture units, then equivalent drained area you take is 1000 square feet. Let's say if you have 200 fixture units, then equivalent drained area which you will take as per procedure is 1000 square feet. And if you have more than 256 fixture units, then equivalent drained area, you will get the equivalent drained area 3.51 square feet per fixture unit. That means every increment in the fixture unit after 256, you need 3.51 square feet per fixture unit. And how did you get this value, I will tell you later. So this is the piping slope which we have used in our project, that is 1/8 inch per foot slope which we have used in here. And now I will tell you how did I get this 3.51 square feet per fixture unit. If you have more than 256 fixture units, for every increment in the fixture unit after 256, you have to use 3.51 square feet per fixture unit. This depends on the rainfall. So since we know that 1 GPM is equal to 60 gallons per hour, so if you want to convert this gallons per hour to cubic feet per hour, you need to divide 60 divided by 7.5. You will get 1 GPM is equal to 8 cubic feet per hour. And we know the rainfall rate in New Delhi is 4.4 inches per hour. If you want to convert this inches to feet, so simply you need to divide 4.4 divided by 12, you will get in a feet, that is 0.37 feet per hour. So now we want to get the how much GPM will be conveyed from the surface, because here if you see that we have a GPM also, so how much GPM will be conveyed from the surface should be converted to equivalent drained area. So that's why we are converting this one. So how you will get this 21.82 square feet, you just need to divide this 8 cubic feet per hour by 0.37 rainfall rate in New Delhi, India. So you will get 21.82 square feet. Now what does it mean, 21.82 square feet? That means 21.82 square feet of horizontal area is equivalent to 1 GPM that must be conveyed from the surface. Or in other words, the 1 GPM collect on 21.82 square feet of horizontal surface if you have a rainfall rate of 4.4 inches per hour. So now we'll go towards the pipe sizing of this combined stormwater and sanitary system. Before proceeding towards sizing, there's one announcement that if you guys join the channel membership, you will get access to exclusive perks like Excel sheets, softwares, and drawings. Whatever I use in the video or in the future videos, you will get access if you have a membership on the channel. And this channel membership is really cheap, around $2 per month. So if you guys want to join the membership link is given in the description, you can join from there. So before proceeding towards the pipe sizing of the combined storm and sanitary system, you can see that this is a combined system we have in here. This is a sanitary drainage piping line, and this is the stormwater line, and here it's combined together, and same thing over here. And one thing you need to understand about the leader pipe and the sanitary drainage pipe. So let's me go to the piping section and explain you here. So as you can see here, this is the combined stormwater and sanitary drainage system. This is the soil stack pipe, and this is the runout from the stack, and this is the main combined storm, this main combined storm and drainage pipe. And you can see that this is the leader pipe for the storm water, and there we have a trap, and then we have horizontal pipe in here. It is important to understand this thing before proceeding towards the pipe sizing. So you can see that the stormwater connection should be at least 10 feet downstream from any branch of the building drain. As per the code, you have to maintain minimum 10 feet distance between the soil stack and the stormwater pipe. So now proceed towards the sizing of the system. And one more thing you can see in here, that this is the roof over here, and this is the roof drain through which water will be drained down. And this is basically a primary scupper, and here you can also see that we have secondary scuppers. These are the secondary scuppers installed in the parapet wall. These are the parapet walls. In case this drain is blocked or clogged, in that case water will drain down from the secondary scuppers, as you can see in here. And these scuppers are installed normally 2 inches above the roof level. So first we'll start from this point, and we'll go up till point Q. So we're gonna start from this point. You can see that this is the stack P2 over here. This is the stack we're talking about. This is the stack pipe, and this is a horizontal run out from the stack. So there we have a stack with 256 fixture units represented by P2. So pipe P2, 256 fixture units. Since we said in here that 256 fixture units, if we have less than 256 fixture units, then equivalent drained area we get is 1000 square feet as per code. So 1000 square feet we have to use in here. But before that, I forgot to tell you how did you get this 3.51 square feet per fixture unit. So since we know that 1 GPM conveyed to 21.82 square feet of the horizontal surface if you have a rainfall of 4.4 inches per hour. So this point 161 you need to multiply with this area which we got here is 21.82. And how did we get 0.161? So every fixture unit after 256 required 0.161 GPM. So that's why we write 0.161 into we talk about 1 GPM is 21.82. Once you multiply these two, you will get 3.51 square feet per fixture unit, and this will be used only if you have fixture units more than 256. Then each fixture unit drainage area you will get by 3.51 square feet per fixture unit. If you have less than 256, less than or equal to 256 fixture unit, then you will get by this procedure you have to get 1000 square feet drained area. Since we have 256 fixture unit in here, so we are going to use this 1000 square feet area. You can see that drained equivalent drained area is 1000 square feet. So now the reference table here which we have to use is 6-3 to get the pipe size. Since this is a stack pipe and we have more than 3-story building, so this is the 6-3 table. There you see 3 columns in here. If you have seen my drainage pipe sizing video or drainage system design, I have used the same table 6-3 and 6-5 for drainage system sizing for the stacks and the runouts. If you have not seen that video, I will give the link in the description below. You can watch it. So since we have more than 3-story building in height, so we have to use this column in here. So how many fixture units we said? 256 fixture unit in here. So 256 fixture units. 256 fixture units is this is 60 and this is 500. So 250 in between them, so we'll go for the higher value 500, and if you will check here is 4 inches. So that's how we got 4 inches pipe size in here. Then move to the section A. Section A is basically the runout from the stack. This is basically a runout from the stack. So we have to use table 6-5 to get the pipe size. We know the fixture unit at point A is also 256. It's same. So this is the runout. So we're going to use table 6-5. So this is table 6-5 which I'm gonna use. Since we know that the slope which we have used here is 118 inches per foot, and fixture unit is how, so we have to follow this column 18 inch per foot slope. 256 fixture units in between them, so we'll go for the higher value 390. You check the pipe size here is 5 inches. So the pipe size from the stack to the runout to the main pipe is so this section A is 5 inches, this using table 6-5. So now we'll go to this is stormwater pipe having a drained area of 3500 square feet. Surface drained area is 3500 square feet, and then we have a trap in here. As I talked here about the trap, this is a leader pipe, this is a trap, and this is a horizontal pipe. So first we'll talk about the leader L2 before trap. This is the leader L2 having 3500 square feet. You can see in here. So we have to use table 7-1 to get the size for this L2. So I'm gonna use 7-1 table, and since we are talking about the leader drained area, so we're gonna use this column, and we said that 3500 square feet. So 3500 square feet is in between 2200 and 4600 square feet, the leader drained area column. So we'll go for the higher value of 4600. So if you check the pipe size in here is 4 inches diameter. So we have to use 4 inch here. So after the trap, you see the horizontal pipe here. This is represented by B. This is represented by B. So 3500 same equivalent drained area at this point. So we have to get the size from the same table 7-1. But this time we have to use 1/8 inch per foot slope column, because this is the horizontal piping drained area for the various slope. Since we know our piping slope is 1/8 inch per foot, and 3500 is in between these two, 3340 and 5350. So we'll go for the higher value, that is 5350. Then this is basically a fixture units. So if you see over here to the left side, the pipe diameter is 6 inches. So that's how we got 6 inches pipe size in here for section B. Now if you see the section C, it is the sum of the flow from the point A and the B. That's why I have written here is C equal to A plus B. Now if you check the drained area at point A is 1000 square feet. We already converted 256 fixture unit to 1000 square feet, and this one is already in square feet, equivalent drained area in square feet. So total it will be 4500 square feet at point C. How we get this 256 fixture unit equal to 1000 square feet, we already talked in here. So total now here is 4500 fixture unit. It is a combined system for stormwater and sanitary system. So we're going to use 7-1 table to do the pipe sizing for at point C or section C. So C section 4500 square feet, use table 7-1 again. So 4500 square feet is in between these two values. So we're gonna use the higher value 5350 fixture unit and check the pipe size in here. Again, this is horizontal piping, so we are using 1/8 inch per foot slope. So 5350, the pipe diameter is 6 inches, so we have used 6 inches in here. So in the same way you have to do for other pipes in here, like 180 fixture unit, 4000 square feet, and then at point F it will be the sum of D and E. And then how you will get for G, it will be the sum of C plus F. And then same way you have to do for this P4 stack, then horizontal run from the stack represented by H, and then P3 stack, and then horizontal run is represented by I, and then you have J over here, and then at point K it will be the sum of G plus J here, that is G plus J. And then you have to do for this one, and for this GPM you have to use since we talk about 1 GPM conveyed equal to 21.82 square feet, so equivalent drained area you just need to multiply 120 with 21.82, you will get the drained area for this one. So now I'm talking about this last one over here. So I will do the sizing for stack P5 first, having 400 fixture units. P5 400 fixture units. So this is the stack P5, so we're going to use the table 6-3. So more than 3 story we have to use again, and 400 fixture units in between 60 and 500. So we'll go for higher value 500, and we'll check the pipe size is 4 inches. So P5 is 4 inches. Again we have the horizontal run from the stack, that is represented by N. So for horizontal run out from the stack we have to use table 6-5. You can see in here again same fixture units from the stack. So 6-5 maximum per visible fixture unit load for this one you can see in here. The slope for the pipe is 1/8 and 400 fixture units. So we have 390 and 700. So we go for the higher value 700, that is more than 390 fixture unit, and you will check the pipe size here is 6 inches, having 1/8 inch per foot slope. So here you can see that 6 inch pipe size we have used in here. Now next is O, that is coming from the sump having 100 GPM drain from that point. So this is 100 GPM, we know that. So we are going to use 1 GPM required one fixture unit over here. So 1 GPM required one fixture unit in here. So 100 GPM required 100 fixture unit in here. So we have used 100 fixture unit. And again, this is the runout from the sump number 2. So for the runouts, we have to use this table having 1/8 inch per foot slope and 100 fixture units between 20 and 180. So we'll go for the higher value 180, and pipe size is 4 inches. So we have used the pipe size 4 inches here. So next is point P. It will be the sum of point N plus O. P, that is the sum of N O, you can see in here. And if you see the fixture unit which we calculated here is 100, and at this point we have point N is 400, point O is 100, and is 400, you can see in here. So total fixture unit at point P, it will be 400 plus 100, that is 500 fixture unit in here. So again, this is the horizontal runout here. For drainage system, there is no stormwater pipe in here, so we can use table 6-5 to do the sizing for section P. So 6-5, 1/8 inch slope per foot, we have to use this one. And we talk about 500 fixture units, so 390 we have, 700 we have. So we'll go for 700 and check the pipe size, because we don't have 500 in here. So we'll use 700. So 700 pipe size is 6 inches. So you can see in here for P section, pipe size is 6 inches. Now the last section here is Q. Q, it will be the sum of the flow from point M and P. You can see in here M and P. So M, we know that if we already calculated in here, the equivalent drained area for M is 12397 square feet. And for point P, we have fixture units. We don't have the equivalent drained area, so we need to convert this fixture unit into equivalent drained area. So G47 is this value. We directly have the equivalent drained area plus this value. Fixture units are 500. Since we said that if we have fixture unit more than 256, so we require 3.51 square feet per fixture units. So we have 500. So 500 into 3.51, it will be 1755 plus 12397. 12397. Sorry, again. 500 into 3.51 plus 12397. So total here is 14,152 equivalent drained area. You can see in here this equivalent drained area at point Q is 14,153, 14,152 or 14,153 here, which we have calculated here, because we have the equivalent drained area directly in here, but this fixture unit we need to convert this into equivalent drained area. So 500 fixture unit, we know that is 3.51 square feet. Since we have 500, so 500 into 3.51, total 1,700 something plus this one. So total fixture unit is 14,153. Since we know the fixture units now, this equivalent drained area in a square feet, so now we can get the pipe size in inches using table 7-1. So again you have to use this is again the horizontal pipe. This one Q is again the horizontal pipe, so we have to use again this horizontal piping 1/8 inch per foot slope, and then you have to check 14,153 fixture units, and 14,153 fixture units you have to check in here, and you will get the pipe size, that is 10 inches. So this is how you can do the combined stormwater sanitary drainage system sizing. Hello friends, today I'm going to discuss the water distribution system design using booster pump as a source of supply, and this is the Excel sheet which I'm going to use for that purpose. You can see here, and there are other tables which I'm going to use in here. You can see the hydraulic tables also, and this is the example which we are going to cover in this session. So as you can see that we have a water service main line, and this is from the street main. If you see that the building information, it's a 16-story building, so I have write 16-story in here, and the street pressure we need to write here. So this street pressure, how you will get this one? You need to get this from the local authority of your area. Normally they are keeping the record how much is the street pressure, so you need to write in here. So let's say the local authority reported the street pressure is 45 psi in our area. So now the next thing over here, if you see here, this is the street main, and this is the piping which we took from the street main, that is water service line. And then we have a booster pump in here, and this is the suction of the booster pump, this is the discharge of the booster pump. And then from here, this point, we have taken the uh, uh, water hot water heater supply, and this one is supplying hot water, and then this one is supplying cold water. And you can see that we have risers, different risers here. This is the riser 1 represented at section H, and riser 3 represented by section B, riser 4 represented by section C, and riser 5 represented by A, riser 2 is represented by F. So I just divided the each riser and section by sections. You can see here, this is A section, this is B, C section, this is B, and then this is section E, this is section D, this is section G, and then this is section I have divided this into different section in order, because we need to calculate the pipe sizes for each section, and we need to calculate the demand for each section. So the next thing we have to check here is the highest fixture outlet. So highest fixture outlet is 180 feet above the pump level. So we need to write this one in here, because later we have to calculate the static pressure for the highest outlet. That's why we have write this thing here. So next thing is you have to check the highest outlet pressure requirement. Since the highest outlet which we use is the water closet, and it's a flush valve operated water closet, so based on this we have to write the highest outlet pressure requirement. If you see the note in here, that is system, if the system is a flush tank operated, 8 to 15 psi we have to use the operating pressure, and if the system is a flush valve operated, we have to use 15 to 25 psi. Since our case we said that water closet is a flush valve operated, so we have used 20 psi. This second case, 15 to 25 psi we can use, so we have used 20 psi in here. If you can join the channel membership, you can get access to the Excel sheet, MEP softwares, MEP books. You can see the channel membership link is given in the video description. You can click join button to get access to Excel sheet. Whatever the level you select, you will get material accordingly. If you have any thing you want to know before taking the membership, you can contact on the email address given in the video description. Even after taking the membership, you can ask things on the same email address mentioned in the video description. So if you join the channel membership, you can get access to Excel sheets, softwares, MEP books, depending on what level you have selected for the membership. So next thing, we have to check the length of run to the farthest and highest fixture. So we need to write that length in here. So you have to go to your drawing and you have to mark the lengths of each section, riser and everything. So since we know that our water closet is the highest and the furthest outlet, so up to that outlet we have to check the length and we have to write in here. Let's say we got 350 feet is the length of run to the furthest, and the highest fixture is 350 feet. We have to write in here. This is called DLR, that is developed length of run. DLR. Then material, this is also very important. So based on material, these hydraulic tables are prepared. You can see here from table 1 14-1 through 14-12. There are total 12 tables I have used here for sizing. So material for water service into the building, that is a copper K tubing. So if you see here, this is water service, this is the street main, and this one we are talking about, this is of type K copper tubing, material for water service into the building, this copper K. And if you see the other one, material for the water distribution system within the building, is type L copper tubing. So from pump discharge within the building, the piping is of type L copper tubing. So next thing we have here is uniform friction head loss. So we are going to use uniform friction head loss in order to calculate the hot and cold water pipe sizing, and we need to keep two things in mind while we do the sizing of the cold water and hot water pipe sizing. That one is this one is the uniform friction head loss, which we set over here, this one, uniform friction head loss. And the second is the velocity. Velocity has a very prime importance for domestic hot and cold water supply system design. So if you see the note over here, maximum recommended velocity for domestic cold water supply pipe sizing is 8 feet per second. And for the hot water supply, maximum recommended velocity is 4 to 5 feet per second. So we are going to use 5 feet per second limitation in a case of hot water supply pipe sizing, and 8 feet per second in a case of cold water supply pipe sizing. So if you are going for higher velocities, if you are going to design your system on higher velocities, which is not recommended, you will have problems of noise, water hammer, cavitation. So that's why you need to follow this velocity recommendation, because we don't want to create any noise issue, cavitation, and water hammer. So we need to keep these velocities in mind. So we are talking about uniform friction head loss. Uniform friction head loss, normally we are taking 4 psi per 100 foot to 10 psi per 100 foot. So we have taken 6 psi per 100 foot over here, which is like most economical design is like 5 to 6 psi per 100 foot. So we have used 6 psi per 100 foot. So as you are changing this uniform friction head loss, if you move to 10 psi per 100 foot, then your pipe sizes will be smaller. That means less insulation will be used, smaller pipe insulation will be used. That means you are saving the cost on the piping and insulation as well, but you are increasing the pump head. Pump head will be increased if you increase the friction head loss. So let's say if I'm going to change this to 10 psi per 100 foot, you will see that pump head loss will be changed. There will be more pump head loss. Let's say this change is to 10 and pump head loss is increased. There is 115.4 psi. So more power will be used by the pump. So let's change back to 6 psi per 100 foot. Now the next thing which we have to use over here is PRV installed at the pump side. So there we have a PRV installed at the pump side. So obviously there will be a lot of fittings over here also, like maybe there will be some drain cock or something, and there will be a water meter here. So you need to add these values in here also. I added only PRV over here, and this PRV, pressure loss or head loss, I got this from manufacturer or supplier of this PRV. So I need to add this value here, 5 psi. If we have water meter over here, we need to add the water meter head loss here also. So next thing we have to add here is the static pressure for the highest outlet. So since we know that our highest outlet is 180 feet above the pump level, so now we need to calculate the static pressure for the highest outlet. We know that 1 feet is equal to 0.433 psi. So static pressure for the highest outlet is equal to 180 feet into 0.433. In order to convert this into psi, it will be 77.94 psi. Now next thing is the equivalent length of run. Equivalent length of run for this system. Equivalent length of run, it will be the sum of straight piping length, which you can see here, straight piping length, plus valves and the fittings used in this system. So since we don't know the sizes of the pipe, so what we do, we use this note. We are going to use a thumb rule, that is 50% of developed length will be considered as a friction loss for the fittings and the valve. This is a thumb rule. So we know that total developed length for the straight pipe of the fitting is 350 feet. We are going to add 50% of this 350 as a friction loss for the valves and the fittings. So how much our equivalent length of run will be? 350 into 1.5, so total 525 feet is the equivalent length of run. Now the last one over here is the friction head loss. How did we get this friction head loss? Friction head loss you have to get just simply multiplying your equivalent length of run with the uniform friction head loss. Uniform friction head loss is 6 psi per 100 foot, and equivalent length of run is 525 feet. So if you multiply 525 with 0.06, you will get 31.5 psi friction head loss. And what is this friction head loss? This friction head loss is due to the straight pipe length plus fittings and the valves in your system here. So the friction head loss is 31.5 psi. Now the total initial pressure, it will be the sum of A, B, C and D. I have write A here, this one, B, C and D. So we need to sum up all these to get the total initial pressure requirement. So total initial required pressure is 134.4 psi. So now we know that street pressure reported is 45 psi. But in a case of peak demand, you will not get this 45 psi, maybe 5 to 10 psi less. So it is a good practice to take 5 to 10 psi less than reported pressure by the local authority. So I'm going to subtract 5 psi from this reported street pressure in a case of peak demand. So here it will be 40 psi. Now we can easily calculate the pump head, how much the pump head will be. So how we'll get the pump head? We need to this total required initial pressure minus suction pressure at the street main. So if you subtract the suction pressure from the street main to the initial pressure requirement, you will get the pump head. So that means pump head is 94.4 psi, and if you want to convert this into feet, so you will get 218 feet is the pump head here. So if you see over here, the total water supply fixture units which we calculated here, which I will tell you later. Let me just calculate the pump head and total capacity. So the total water supply fixture unit which we calculated here is 4840 fixture unit at this point. 4840 you can see here. So 4840 fixture unit, we need to calculate the pump capacity. We calculated the head, but we need to calculate the demand GPM for this one. So 4840 fixture units. So 4840 fixture units, I will go to this table. If you see the conversion of fixture unit to equivalent GPM, this is for the flush tank, this is for the flush valves. So if you note that after 1000 fixture units, values are same for flush tank and the flush valves. So our case, we have to check for 4840 fixture units. So if you go for 4000 we have and 5000 we have, so we will apply the interpolation formula to get the exact value of the GPM at 4840. So this is the interpolation table which I have. This is a formula which I am going to use, interpolation formula, to get the exact value. So we have 4000 fixture units and we have 5000 fixture unit, and we need to calculate GPM at 4840. So as I'm applying all the values, you will see the GPM calculated here. So we know that for how much GPM we have at 4000 and how much GPM we have at 5000. So go here, 4000 how much GPM, 525, and 5000 we have 593. So 525 and 593. So 525 and 593, it will calculate at 4840. So how much GPM calculated at 4840? 582 GPM. That's how I write 582 GPM, and reference table is 13-4, which I use here, this one. So this is how you can calculate the booster pump head as well as demand. So now we will proceed towards the hot and cold water demand. So after demand, we have to calculate the pipe sizes for the hot water as well as cold water. So here I used only water supply demand calculation for riser 4, which is represented by section C. So in the same way which I'm telling you now, you have to calculate the water supply demand for other risers and other sections of the building. So this is the riser 4 which I'm going to calculate right now, demand calculation. So in riser 4 I got there's a flush there's a water closet of flush valve types, and urinals we have, and the lavatory we have. So we have to write all the fixtures for each riser and section one by one, and then we have to go for number of fixtures. So how many water closet I have? 55 water closets, 15 urinals wall hung, and 42 lavatories. So now we have to calculate the hot water fixture unit and total hot water fixture unit. Now we have to calculate cold water fixture unit and total cold water fixture units, and then combined hot and cold water fixture units. So number of fixtures, I write 55 here. Now I have to get the value of each water closet. So I'll go to this table, demand weight of fixtures in fixture units. So we have a water closet now, and 16-story office building, and this we considered as and we know that it's a flush valve operated water closet. So occupancy is public, flush valve operated, and you see that cold there is no cold water connection on water closets. That's why there is no value in here. So hot there is no connection of hot water, so that's why no value here. So we have only cold water point in the water closet. So value of fixture unit is 10 in a case of water closet with a flush valve, and total fixture unit value is 10. So we are going to write for cold water fixture unit is 10 value, and combined it's also 10. Combined water supply fixture unit value is also 10. So how we will get the total cold water fixture unit? We just need to multiply number of fixture with each fixture unit value. So we'll get the total cold water fixture unit value. So in the same way you have to go for urinals, and how we will get the total water supply fixture unit. We know that 10 value we have calculated here. 10 value, you can see that combined for a total value of fixture unit is 10. So we have write 10 here. So it's the same, 10 into 55, that is 550 total fixture units. So now I'm going to show you for the lavatory as well. Total 42 lavatories we have, and each total 42 lavatories we have here, and in the lavatory we have both hot water as well as cold water connection. So we need to write value for the hot and cold water. So we'll go here in our table 13-3. Now we have to check for lavatory. So lavatory, if you see here, this one is the lavatory, but this is a private, and this lavatory is public. So we are going to use this one, public lavatory. So if you see here, the hot water is 1.5, cold water is 1.5, and total fixture unit value is 2. So we will write here hot is 1.5 fixture unit, cold each fixture unit is 1.5, and combined is 2. So 1.5 into 42, you will get the total hot water fixture unit, that is 63, and 42 into 1.5, that is cold water fixture unit, 42 number of fixture unit into each cold water fixture unit is 1.5, so total is 63 as well. And if you see the combined, we have 2, so 42 into 2, you will get 84 total fixture units. The reason is, so if you see the total hot water fixture unit at riser 4 section C is 63, and total cold water fixture unit at riser 4 is 688 fixture units. So same, if we have right here hot water 63 fixture unit, cold water fixture units are 688 fixture units at riser 4 or section C. And the reason why I have calculated the total water supply fixture unit, because when we do the sizing for this section, that is from pump discharge up till this point where the connection is taken off to the hot water heater, so this line and the water service main will be sized based on total water supply fixture unit values. That is, this is only for riser 4. You need to calculate for every riser and sum up. You need to calculate for every riser this for total water supply fixture unit value and write in here. It is, that is 4840 fixture unit. So you need to size this piping and water service main based on this total water supply fixture unit value, that is 4840 fixture unit. And from this point you have to do the sizing for each section and riser based on the fixture units. That is, cold water fixture unit is the total cold water fixture unit at this point is 4730, and total hot water fixture units are 345. So if you see here, if you sum up the water supply fixture units up till this point, let's check the cold water fixture units. So this riser 5 or section A is 1376 plus we have 688 here and 430 cold water fixture units here, that is 2494 at this point. And then we have to some cold water 860 here, 860 plus 2494, that is 3354. So we have 3354 cold water fixture unit at this point. Now the last one is riser 1, that is 1376 fixture unit plus 1376. So total cold water supply fixture units are 4730 fixture unit, you can see here up till this point. Same way you have to calculate the hot water, it will be 345 fixture units. But as I told you, from this point you have to calculate the pipe sizes and GPM demand based on total GPA, total water supply fixture unit. Just like we calculate for riser 4, you have to calculate for riser 3, 2, 1 and then sum up, and it will be 4840 fixture units. So now next step is we have to go for the cold and hot water pipe sizing, and I'm going to use the hydraulic tables to calculate the cold and hot water pipe sizing. You can see that these hydraulic tables, there are total 12 hydraulic tables which I'm going to use. So let's go to the calculation sheet and let me show you for any riser to calculate the pipe size. So let's check for riser 5, which is represented by section A. You can see that riser 5 represented by section A, and how many cold water supply fixture units we have here, 1376. I'm not going to calculate for all risers demand. The way I have shown you for riser 4 represented by section C, same way you have to calculate the demand for each riser and each section. Otherwise video will be much longer, that's why you have to calculate. This is just a procedure to show you how you can calculate. So riser 5A fixture units, cold water supply fixture units are 1376. Now we need to calculate the demand at this point. So as I told you how we need to convert this fixture unit into demand GPM. So how we'll get this one? I have used the interpolation table as I shown you before. So 1376, this is a cold water. So 1376, so we have 1250 and we have 1500. So this one is for the flush tank and this is for the flush valve. So our this riser contain the flush this water closets with flush valve system operated. So we are going to follow this column, the flush valve. So 1250 demand is 240 GPM and 1500 demand is 267 GPM. So 240 and 267, we have to write here GPM, and this one is 1250 and this one is 1500, and we need to check fixed unit value at 1376. So fixed unit value we have 1376, we need to check the demand. So how much is the calculated demand at 1376 fixed unit? This is the interpolation formula, so which I have used here to get the exact value of the demand, that is 254 GPM. So now we know the demand at 1376 fixture unit. So now we need to calculate the pipe size. So now I have to check the pipe size. So the table which I have used here is 14-9 as a reference table to calculate this pipe size of 4 inches. Now I will tell you how did I get this pipe size of 4 inches. So demand calculated here is 254 GPM. 254 GPM. If you see here 254 GPM. So since if you remember that in the beginning I said that material for water service into the building is copper K and distribution system inside the building is L. So we have to check this L copper tubing, 254 GPM. So this is the L copper tubing and 254 GPM. If you see that 240 GPM we have 260 GPM, we don't have 254 GPM, so we will interpolate the value for 254 GPM. If you see that 240 GPM value is this is the velocity column and this is the head loss column for copper L tubing. So 240 GPM velocity is 6.42 and 260 GPM velocity is 6.95. so we will use interpolation formula to get the value at 254. So 240 and 260 we have 6.42 velocity and 6.95. 6.42 and 6.95 at 240 GPM and 260 GPM we need to calculate at 254 GPM. So how much is the velocity calculated at 254 GPM? That is 6.79 feet per second. 6.79 feet per second, as you can see here. So since this 6.79 feet per second is less than 8 feet per second, which we said here in the beginning, so the pipe size which we selected 4 inches here is okay, we can use 4 inches pipe size. Now we have to calculate the head loss also. We use the uniform head loss of 6 psi per 100 foot. So now we need to calculate the head loss also at this pipe segment or riser 5, which is represented by section A. See, same way we have to calculate the head loss. So we will just write the GPM here, interpolation table, and we calculate the head loss. We'll go here and now we'll calculate the head loss. 240 and 260. 240 copper L tubing. How much is the head loss? 1.9 psi per 100 foot, and 260 head loss is 2.1. So 1.9 and 2.1. 1.9 and 2.1. So calculated head loss is 2.04 psi per 100 foot. So 2.04 psi per 100 foot. So this is how you have to use hydraulic table to get the pipe size for cold water pipe sizing. So let's go for another riser. Let's check for this riser 3 plus 4 plus 5, which is represented by E, as you can see here in the drawing. This pipe segment which we are going to calculate now, this is riser 5A, this is 4, and this is 3. So at this point it will be the sum of section A, B and C, which is represented by, and also as well as D. So D is basically the sum of D is basically the sum of this riser 3 and 4 is represented by D. So if you see that total fixture units at this point section E, it will be, so if you see the sum of 3 and 4 riser is cold water supply fixture unit 430 and 688, that is 1118, which is written here 1118 represented by D. And then we have to add this 5A cold water supply fixture unit 1376 plus 1376, so 2494. So total for cold water supply fixture unit at section E is 2494. So we need to calculate demand first, 2494, in order to get the pipe size at this section, which is represented by E. So you can see here, I just sum up this, and in order to get the value, so 3 plus 4 is represented by D. So and we get the value of total fixture unit is 2494. Now we need to convert this into demand GPM. So how we'll do this one? So we will I will use the interpolation table again, 2494, and if we go here and we will check, we have 2250 and 2500. So 2250 fixture unit, 2500 fixture unit, the value is 348 and 375. 348 and 375. So 2250 we have 348 and 2500 we have 375. So how much is the GPM calculated if we have a fixture unit of 2494? GPM calculated is using interpolation formula 374 GPM. So we have right here 374 GPM. So demand is done. Now we have to calculate the pipe size again, and then velocity, and then head loss. We need to confirm the velocity should be less than 8 feet per second. So now we need to calculate the pipe size first for 374 GPM. Reference table we use is 14-10. So this is the 14-10 table, and how much GPM we set? 374 GPM. So 374 GPM. So one thing I need to tell you first, if you see that 374 GPM is also available in here, but if you move to the copper L tubing and check the velocity is 9.36 at 350 and 10.70 at 400. So 374 is also available in here, but if you see the velocity is higher than recommended velocity, it exceeds the limit. That's why we are not using this 4-inch pipe size. Head loss, although the head loss is okay, but velocity is exceeding, so we are not going to select 4-inch pipe size. That's why we have selected 5-inch pipe size, table 14-10. So if we go here and we check 350 and 400, so we need to check at 374 GPM. So 350 copper L, type L copper, velocity is 6.01, and 400 6.87. 6.01, 6.87. This one is at 350, this one is at 400, and we need to check at 374. So 374, if we check the velocity calculated is 6.42 feet per second using the interpolation formula. So we have right here 6.42 feet per second. Now we need to calculate the head loss as well. Same way, we go to 14-10 table. 350 head loss is 1.3, 400 head loss is 1.7. 1.3 and 1.7. Head loss is 1.49 psi per 100 foot at 374 GPM. So 1.49 psi per 100 foot at, so if you notice that the velocity 6.42 is less than 8 feet per second, and the head loss is 1.49 psi per 100 foot. So both values are less than our recommended values which we said in the beginning. So the 5-inch pipe size selected for 374 GPM is correct here. So now in the same way you have to calculate the pipe sizes for other sections. Now let's check for the hot water pipe sizing, how you will calculate the hot water supply pipe size. Let's take one example for this one. So we are going to calculate the hot water pipe size for section G. So if you see that this is the section G, and hot water supply fixture units at section G are 249 fixture units. So we have 249 fixture units over here. Now we need to calculate the GPM for this hot water supply pipe sizing. So how we'll get the GPM for this one? So same, we have to use 13-4 table to get the GPM. This table we have to use for fixture unit to GPM. So fixture unit over here are 249. This is for the flush tank, this is for the flush valves. 249. So 225 and 250 over here. But at this point, for hot water pipe sizing, you have to use the flush tanks, not the flush valves column, because we don't have a water closet and urinals included in the hot water piping system. So we have to use flush tank over here this time for the hot water pipe sizing. So we have 225 and 250, that is 70 and 75 GPM. 70 and 75. $225 and 250. 225, 70 GPM, 250, we have 75 GPM. We need to check at 249 fixture unit how much the GPM value. So it's same 75 GPM, so we are going to use 75 GPM here as well. So here we have used 74 GPM, so 74, 75, so we will change this to 75 GPM. So we are going to use 75 GPM here. Now we need to check the pipe size at this GPM demand. So how much pipe size, hot pipe size will be. So table which I have used here is reference 14-7. So I'm going to use this table. Demand is 75 GPM. So we have a demand of 70 GPM here, and copper L, type L copper. If you see 70, we have 4.70, and the 80 we have 5.37. 70 we have 4.70 velocity, and 80 we have 5.37. Four point 5.37. $70 and 80, and we need to check at how much GPM. 75 GPM. So velocity is 5.04 GPM, 5.04 feet per second, sorry, 5.04 feet per second. So recommended velocity is 5 feet per second for hot water system. As we said, it is 5.04, is almost 5 feet per second. So we can change the size to 3 inches, but it's okay to use 2.5 inches because it's almost 5 feet per second. So that's why we have used 2.5 inches pipe size in here. So in the same way, you have to calculate the pipe sizes for all other sections. You have to calculate the pipe sizes for the sections, the as I have written here in the table. So the last thing I have to tell you over here is you have to calculate the pipe size for this section from booster pump discharge up to the point where connection is taken off to the hot water heater. So this will be sized based on total water supply fixture unit, as I mentioned you earlier. So total water supply fixture units over here are 4840 fixture units. So I need to do the pipe sizing for 4840 fixture units. So let's go to the calculation sheet. We calculated the total water supply fixture units are 4840. We already know the demand at this point is 582 GPM. So let's get the size. Let's get the size of this pipe size. Let's get the pipe size for this demand. So this time I'm going to check the table, hydraulic table. Over here it's a 5-inch table, and 5-inch table, if you check the demand, here is 550 and 600. So 550, we have 550. If we check, the velocity is copper L tubing. Since this is again inside the building, this so we have to use copper, type L copper. So 550, the velocity is 9.45 feet per second, and 600 velocity is 10.3 feet per second. So again, this velocity is higher than recommended 8 feet per second, so we are not going to use 5-inch pipe size. So we'll go to the next table, 6 inches, and then check the demand 550 and 600. 550 and 600, type L copper, velocity is 6.57 at 550 and 7.17 at 600. So 6.57, and let's interpolate and get the exact value at 582. So 6.57 and 7.17. 7.17. This is at 550 GPM fixture units. Sorry, this value we have to check the velocity. So 550 we have 6.57 velocity, and 600 we have 7.17 velocity. We need to check at 582 GPM. So how much it will be? So velocity calculated at 582 GPM is 6.95. So 6.95 is the velocity calculated in here, feet per second. So the velocity calculated here is 6.95 feet per second at 4840 fixture unit, and with the pipe size of, how much is the pipe size we selected here is 6 inches. So 6-inch pipe size. So 6 inches pipe size. So this pipe segment from discharge, booster pump discharge up to this point, it will be 6 inches. So same water supply fixture unit you will have here, 4840 fixture unit. So same pipe size we can use in here. So this is how you can design your water supply system using a booster pump as a source of supply. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe, and don't forget to press the bell icon. And one more thing before ending this video session, if you can join the channel membership, you can get access to the Excel sheet, MEP softwares, MEP books. You can see the channel membership link is given in the video description. You can click join button to get access to Excel sheet. Whatever the level you select, you will get material accordingly. If you have any thing you want to know before taking the membership, you can contact on the email address given in the video description. Even after taking the membership, you can ask things on the same email address mentioned in the video description. So if you join the channel membership, you can get access to Excel sheets, softwares, MAP books, depending on what level you have selected for the membership. So this is the end of this session.